Right now, your brain is processing a live visual feed capable of distinguishing up to 12 million distinct colors. All of that visual processing power is packed into a biological sphere averaging just 2.3 centimeters across. Think of this tiny organ as a sophisticated camera. The dark circle in the center, your pupil, acts as the aperture, letting light in. Surrounding it is the iris, the pigmented muscle that physically expands and contracts to control exactly how much light hits the internal sensor. Looking at this side-by-side comparison, the mechanics are virtually identical. Just as a mechanical camera lens focuses light onto a piece of film, the eye's cornea and lens bend incoming light directly onto the retina. This innermost layer catches that light and immediately translates it into electrical impulses, firing them down the optic nerve to the brain. Strip away the biology, and the eye is simply a machine designed to capture, bend, and translate the physics of light. But where this organic machine outperforms most traditional cameras is its ability to actively change its own internal lens power on the fly. This dynamic mechanism is known as the power of accommodation. Watch the eye handle distant objects. Ciliary muscles relax, thinning the lens to increase focal length, guiding parallel light onto the retina. As objects move closer, these muscles contract, thickening the lens. This reduces focal length, bending diverging light to hit the same target. There is a physical ceiling to this mechanism. For a person with normal vision, the maximum accommodating power caps out at around 4 diopters. Beyond that limit, the focal length simply cannot be altered. Because this dynamic focusing system relies entirely on the constant flexing and pulling of living tissues, it is highly vulnerable to mechanical failure. Often, a system failure starts with the basic geometry of the eyeball. Even a millimeter of anatomical mismatch in the eye's depth will cause the focal point to completely miss the retina target. Take myopia, commonly known as short-sightedness. People with this condition have no problem reading a book close up, but struggle to focus on distant objects. In a myopic eye, the housing is elongated. Light rays converge too early, creating a focal point falling short of the retina. To correct this, a concave lens is placed in front. It spreads the light out slightly, pushing the internal focal point back to intersect precisely with the retina. On the opposite end of the spectrum is hypermetropia, or farsightedness. Here, the distant view is crisp, but objects sitting right in front of the face become entirely blurred. In this scenario, the eyeball is too short. Light passes through the lens but fails to converge, projecting a focal point behind the retina. The solution requires a convex lens. Pinching the incoming light rays together, the artificial lens pulls the focal point forward to rest exactly where it belongs. A geometric error in the biological structure is neatly neutralized by applying an opposing geometric correction in the form of glass. But even if the eye is perfectly shaped at birth, it cannot escape the physical degradation caused by aging. Over decades, the internal ciliary muscles gradually weaken and the biconvex lens begins to harden. This results in presbyopia, a direct loss of the eye's power of accommodation. Practically, this means losing the ability to read or write without help. The biological mechanism can no longer bulge the lens enough for close-up tasks, forcing us to rely on external reading glasses to do the focusing work the muscles no longer can. Watch how this clear disc slowly turns opaque. This demonstrates a much more severe material failure known as a cataract. The naturally transparent proteins inside the biological lens physically erode and clump together, turning the clear window completely cloudy. External glasses cannot fix a frosted window. Correcting a cataract requires surgical escalation, opening the organ itself, extracting the eroded biological lens, and replacing it entirely with a clear synthetic one. As the living machine slowly wears out, our medical interventions must scale right alongside it, moving from external glass patches to internal hardware replacements. Despite being our most intricate sensory organ, the human eye remains bound by the limits of anatomical flaws and the friction of time. Yet, because we have meticulously mapped every muscle, fluid, and curve of this structure, a biological breakdown no longer dictates a permanent loss of vision. Whether we are recalculating the focal length to correct a misshapen eyeball or swapping out a degraded lens for a manufactured replacement, artificial engineering serves as the ultimate system patch. By mastering the physics of light refraction, we have built the tools to bypass our biological limits, ensuring our connection to the visual world remains unbroken and perfectly in focus.